next speaker will be Cristian Villavicencio. He will be talking about external magnetic field effects on nucleons from QCD sum rules. So,
thank you, Gorat. Let me see.
You can share the screen.
Okay, here it is. Thank you very much. Once again, it's nice to be in Afonagüe, virtually or or really. This is a work we published the last year in collaboration with Marcelo Leve and Renato Zamora from Chile, and Cesario Dominguez from Cape Town, and Luis Hernandez from Mexico. Well, our motivation is the intense magnetic fields produced mainly in the relativistic heavy ion collisions, which can be reached. It can reach up to 1 GeV squared. It's a really huge amount of strength of magnetic field. In fact, even more than the most known magnetized objects in the universe, that are the magnetars. And there are many models trying to study such systems of high temperature and high magnetic fields and high density and high magnetic field indeed, but all have their advantages and disadvantages. One of the advantages that we use in this using finite energy sum rules is that we can reach precisely these amounts of magnetic field strength. Usually, most of works use Landau level expansions, and they are valid for extreme values of magnetic field, and extreme values, I mean, bigger than the 1 GeV squared. So, but of course, there are many other treatments that are very good. Okay, so I will start with the short introduction of finite energy sum rules, but the last talk already makes some introduction of sum rules. I will explain nuclear finite energy sum rules at vacuum, and then the introduction of magnetic field and the results. Okay, for example, if we start with a correlation of two vector currents, we will obtain after Fourier transformation this is the composition of the form factor with the longitudinal part and transverse part. So we can obtain the spectral function of those form factors as the imaginary part. And if we plot some form factor, for example, it reproduces some channel with described resonances. For example, this is a point like with a small width, then start the hadronic resonances, and then the higher resonances overlapped, producing a continuum here. And there is a natural threshold named the hadronic continuum threshold that divides this distinguishable resonances from this hadronic continuum. And in QCD sum rules, this is the usual contour. Consider the Pacman contour. So in the energy squared, plot, complex energy squared plot. We have there is a branch cut in the real part, yeah, the S is Q squared, and we can use the quark hadron duality that says, okay, the hadrons live in the real axis, and QCD lives in the complex plane. So using the Cauchy theorem, the contour here, no, sorry, this is the real part. This is the imaginary part of the form factor studied, correspond to hadronic sector, and on the circle correspond to QCD. And this function here in red, K, is a kernel function or weight function that in the finite energy samples are powers of the energy momentum at S. So for example, in Borel-Laplace, there's this an exponential function. And the advantage is that, in fact, as Marcelo mentioned recently, this power cut the operational product expansion series. So at some point, the series in operator is truncated depending on the power of this weight function, this kernel. So, for example, if we neglect masses, the expansion in S can be described in terms of operator and accompanied with these Wilson parameters. So these Wilson parameters usually are logs of S and or some powers of S. Like we can see that if we integrate in the contour here, depending on the power of S, this function here vanishes for S higher than, for a power here of S higher than N or N minus 1. Okay, what happened with the nucleons in vacuum? The correlator are in terms of the nucleon interpolating function. They are called a nuclear currents that in terms of the hadronic sector is basically a nucleon field multiplied by a coupling named the current nucleon coupling. In expressions in terms of quarks, this corresponds to the interpolating function. So there are 3 quarks coupled in the inside. Okay, and it can be decomposed into components. Okay, one proportional to Q slash, and the other one is the scalar. So basically, we can see the first one is the perturbative. Well, we do not include the radiative corrections. Then the chiral condensate, 4 condensates, gluon condensate, mixed condensates, and so on. So in vacuum, the first correlator, you can see that the first term is proportional to the log of S minus S squared. Then we have the gluon condensate proportional to the log, the 4 quark condensate, and then continue the series in terms of operators, higher dimension operators. And the other correlator form factor include the chiral condensate, the mixed quark gluon condensate, and so on. So if we apply the kernel equal to 1, actually we can remove all these condensates, and also here all these condensates. Those terms survive. And here up to the 4 quark condensate survive. In the hadronic sector, this is the simplest, the correlated of 2 nucleons. So it's expressed in the coupling to the square on the simple propagator. Okay, and applying the sum rules with the kernel equal to 1. This is the 2 sum rules we obtain, and with some usual approximations for the mixed condensates, this is what can be obtained. In the final energy sum rules, the hadronic continuum threshold is one of the parameters that needs to be obtained. Usually in other sum rules like Borel sum rule, this is it's obtained by looking at an stability sector. Here is one of the parameters to be obtained in the sum rules. So now, if you include magnetic field, first of all, the structure of the correlator will change. So we have, in terms of Clifford, the composition of gamma matrices, we have one scalar, one pseudo-scalar, it's supposed, but it doesn't appear, vector, axial, and tensorial structure. So the scalar is one of the structures we're going to consider. In the vector, the composition, we can sub-decompose in the external momentum parallel to the magnetic field, perpendicular to the magnetic field, and contracted to this, basically to the F mu, the electromagnetic tensor. And we will not consider this one, and one of the tensor structures will be considered, basically the one proportional to F mu. Now, what changes here are the propagators. There are magnetic field dependent propagators, which are decomposed in some local part, and this non-local part is known as the Schwinger phase. And this can be expressed in terms of powers of the magnetic field. So, for example, this expansion up to the level we need, we just need the
5 more minutes. Yeah.
Okay, thanks. The magnetic field linear and quadratically contributions. So basically, those are the diagrams we have to add in the sum rules. This double line corresponds to the quadratic ones. And there's something special with this expansion magnetic field, that we can also cut the series. So it acts like expansion in the operators product expansion. It also works with expansion in magnetic field. So there's some advantage is that we can use, and we can before integrating, for example, the typical one loop diagram up in here will be some denominator S and these corrections to the mass quark, and X are the Feynman parameters. So if we integrate on the contour before, we can get a simplified expression to integrate after in the Feynman parameters. But this theta here is a function that says it is 1 if n, capital N minus n is bigger than 1, or 0 if not. The other function that appear with the logs, and is most simple to integrate first in the contour and then integrate the Feynman parameters. So with the magnetic field also truncates the OP series. So that's why we know how many terms we need in the expansion of the propagator in the magnetic dependent propagator, and how many diagrams we need, in fact. So this is an exact truncation, not an approximation. Okay, this is the result with all we obtain 4 sum rules. In blue, there are inputs that we know from other works. The gluon condensate, the quark condensate, the quark mass, also we know from previous works. And thus, lambda, the hadronic threshold, S, and this V is something known the proton velocity, something that remains the velocity of a massless particle that will be different from 1 in the case of effects, external effects. And in particular, this object that is it's known of the polarization of a quark condensate. So first of all, we need to see the hadronic threshold, because we're going to put some limits to our model of how much magnetic field it's valid to. So for example, protons and neutrons behave differently as expected, and the limit will be about 1.9 GeV squared, because after that there's the appearance of the nucleon 1.4 GeV. It's about 1.88 GeV squared. So this is our
1 minute.
limit. Okay. Okay, we obtained the lambdas as well, what we need for the works. The transverse velocity, that is a good indicator that everything is fine, because it must be less than 1. So here is the polarization of quark condensate, and we can compare with other works. Most of works consider this quantity, that is the susceptibility of this condensate, as the same as U and D. So we respect the difference between up and down for protons and neutrons, and in fact we obtain different values, all in the range, acceptable range. And if we see that this is mostly constant here, we can put this as an input and obtain the nuclear mass. And the nuclear mass evolution with magnetic field coincide with other works, in particular with lattice, for example. And this is the main difference between our works and the others. So the difference about protons and neutrons, so most of works considered equal behavior. So now we have a split in the behavior, and in fact we can see that the mass of the proton grows and the neutrons decrease with the magnetic field. And then it starts to grow, but for higher values. The definition of the mass differs in different contexts. This is the definition of the minimal energy, which include the anomalous magnetic moments. In this case, both masses decreases, but the proton masses start to grow earlier. So in summary, well, the sum rules with magnetic field cut the series in B, as well as it does with the OP series. We have different flavor values. This is most interesting. Okay, all these quantities. The magnetic susceptibility of quark condensate is almost constant. Most of works, the works consider this as constant. we proved that it's almost constant for the very large values, and it's in good agreement with other approaches. So our next step is consider an axial coupling, the nuclear axial coupling, to obtain this value, and include the variant density effects to explore the axial coupling in the case of neutron stars. Okay, thank you very much.
Okay. Thank you very much for your exposition. We have time for one short question. Jörg, please. Let's see.
Thanks for the talk, Christian. I indeed only have a very short question. It's concerning the input of that you're using after evaluating the sum rules that you have shown us. These are the condensates, of which I suppose the quark condensate must be one of the more important ones. And you mentioned that their magnetic field dependence is known from other works.
Yes.
What do you mean by that? Are these experimental fits? Are these lattice simulations? Are these models?
Yeah. A good question. I have no time to explain where we get all these inputs. For example, the quark condensate, the magnetic dependence after from lattice results from the group of Bali et al. But this is mostly studied with in many works, and the most coincide with lattice. So this is a secure number. The gluon condensate, in previous work, we obtained it with some rules that depending on the inputs, it can grow and can diminish, but it's almost a small quantity. And there are also lattice group of Massimo Delia that obtain it almost constant. So we keep it constant. The mass quark, we get also the value of the mass quarks in previous works, but it doesn't have an impact in the behavior, as well as the nuclear masses. It does not change much. The nuclear masses can be obtained in from different works. We tried several, and there's not much impact in these quantities.
Okay, so the main influence comes from the magnetic field dependence of the quark condensate that you took from Bali at lattice. Okay, thanks.